Assalamu alaikum and welcome to lecture number 18. In this lecture we are going to do numericals on the properties of the LTI systems. We have completed all the properties which we are going to study in this course. So in this lecture we are going to have some numerical problems which are based on those properties. So here we are given the impulse responses for LTI systems, and we have to find the step responses. So I hope you understand that in case of discrete time system, we can say step response or Sn equals to summation k running from minus infinity. So this is the equation for finding the step response when you are given the impulse response for the discrete time case, and this is given the this is how to find the step response when we are given the impulse response in continuous time case, right? So if you look at the first problem, what is this here? Impulse response is equal to 1 by 2 power n u of n, right? So you all understand what does u of n signifies here. It signifies that n cannot have negative values. So if n cannot have negative values, then we multiply it in those cases with the step function u of n, right, for the discrete time case. Okay, so that means this response exists from 0 up to infinity, right? Because this is multiplied with u of n, so that means n cannot have negative value. So we have to find the step response for this signal, right? This response. In the second part, we are given h of t equals to e power absolute of minus absolute of t, right? So you understand this is for the continuous time case, and you probably know what does e power minus t absolute tells, right? So definitely you understand this is exponential signal, but whether this exponential signal is growing or decaying, right? So if we have absolute and then we have minus here, that means this is basically exponentially decaying signal for both values of t. That means for the values of t which are from 0 to infinity, or the values of t that are from 0 to minus infinity. So we can write this in piecewise form, and we can say basically this signal equals to e power, because whether e is positive or negative, you understand absolute means you get positive value, and here it's negative. So that means irrespective of whether t is positive or negative, right, in both cases it is exponentially decaying. So I can split it into e power minus t, e power plus t, and this is for the case when t has values from minus infinity up to 0, right? So it has this form, and the second part of it will be e power minus t, and now we'll say this is basically t ranging from 0 up to infinity, right? So we can split it into two, and we can easily observe that because this signifies, the absolute sign signifies that whether it's a positive or negative, it we will have positive here, and the negative sign says, so that means whether t is positive or negative, this signal is exponentially decaying signal. So this is how we can split it, and as a homework I give you to find, because you have the equation, so you can find it the step response. The third signal is again a the third response is again a continuous time response, and here the response is that h of t equals to impulse of t minus 1 unit shifted. You understand this minus this is plus 1 basically, right? This minus is from formula, so this is plus 1, and plus 1 indicates that this is the delayed by a amount of 1 unit. So let's do this problem. So to find the step response, we can easily write as s of t equals to, right, integration, and this is from minus infinity up to t, and this will be impulse of tau d tau, and minus integration from minus infinity up to t, and this is impulse of tau minus 1 and d tau. So if you look at carefully and recall, this is basically the equation for the step, right? Because in the starting lectures of signal and system, we said the relationship between the step function and impulse is that if you integrate from minus infinity up to t the impulse, you get the step function, and similarly if you take the first derivative of the step function, you get the impulse. So again, similar arguments apply to this one, so that means we can say basically this is equal to u of t. Okay, this is u of t, and this is minus this 1 unit shifted u of t, so u of t minus u of t minus 1. Okay, I hope you can go for the part A and part B by yourself, right? So if you have any confusion, you can discuss in the live session. So here we are considering again a problem that we have already considered while we were doing the while we were starting the convolution sum. So this system was given there, and we found the output for this system. So again, now here we are going to find the inverse system, right? So this is the system. Okay, we say this is the input signal, right, which is transmitted from a communication channel, and y of n is the received signal at the receive end, right? So when we transmit it, basically it was a, if you recall, a two path communication channel where the input signal x of 1 was received directly, whereas its delayed version, delayed and attenuated version, this one, is received after, say it was collided with a building, and after that it's reflected and received. So now our problem is to find the causal inverse system that recovers x of n from y of n, right? So that means we want to discard this one because our original signal is this one, but it is somehow distorted due to the echo, which is the delayed version, delayed and attenuated version of the same signal. So because here we are not given the impulse response of the system, so first step will be that we find the impulse response of this system. So you understand what is impulse response? Impulse response is the output of the system when the input is impulse. So that means we can put here h of n. So h of n of this system as defined can be obtained by impulse of n minus a times impulse of n minus 1. So that is our system, right? And we have to design an inverse system that recovers xn. one mistake here. Basically this is plus sign here. Okay, so it will be this one. So now we have find the impulse response of the system. Now we need to find the impulse response of the inverse system, right? So you understand, if two systems having impulse response h of n and another system that has impulse response of h of n inverse, because right, h inverse n. So if they are inverse, then the convolution of the two must result into impulse of n, right? So that's we have done already when we were talking about the inverse systems, right? So if two systems are inverse, then if we cascade them in series, right, so we get whatever at the input we get at the output. So the condition for the system to be inverse is that the impulse responses, if convolved of the two, they will result into this. So if this is the case, then we say the two systems are inverse of each other, right? So now let's use this logic and let's proceed with it. So we know h of n. Okay, so n convolved with h inverse of n is same as h inverse of n convolved with h of n, because the convolution holds the property of commutative. So based on that we can say, okay, the next is the distributive property. So h inverse of n convolved with h of n means, because h of n equals to this, right? So that means I will convolve this and again convolve this, that is the distributive property. Okay, so I can write it like this, and because the two systems, they are inverse, so that means this must be impulse of n, right? So this should be equal to impulse of n. Now if again we use the property that you understand, impulse is the identity of the convolution operation, right? Convolution is also operation just like addition, subtraction, multiplication, etc. So the identity of like multiplication is 1, so you multiply anything with 1, you get the same thing, right? Or for the case of addition, we have 0 is the identity of addition, right? So if you add anything with 0, you get the same thing. So again, because this we know already, so that means multiplication of this will result into convolution of this will result into this same thing. So that means we can write h of n, h inverse of n, we get the same, right? Again from here, because we know the property that if we convolve anything with impulse, we get the same thing. If the impulse is shifted, this will be shifted, right? If the impulse is scaled, this will be scaled. So that means I should get a h inverse of n minus 1, and this is equal to impulse of n, right? Now we are given that find causal inverse system, right? So when it's causal, so what was the definition of the causal, right? So for the case of causal, we know that h of n will be 0 when n is less than 0. That means n cannot have the negative value, right? So that means for negative value, this must result into 0, and for positive value, let's find the value. So for example, if n equals to 0, so h inverse of 0 will be equal, right? You understand? Or I should write a sentence here. Okay, so we are finding the causal inverse system. So you understand, for if the system is causal, and the output will be 0 when n is negative. So that means we can have these values only. Okay, n is equal to or greater than 0. So starting with n equals to 0, so by putting value here 0, if I put 0, so 0 minus 1 is minus 1, and this will come 0. So if you look at this one, so I get h inverse of n equals to h inverse of, not n, in fact h inverse of 0, so this will be right. And because this is causal system, so negative value argument will result into 0, so this will be 0, so this is equal to impulse of 0 is basically 1. So that means h inverse of 0 equals to 1. Similarly, by putting n equals to 1, 2, 3, I get, okay, so h inverse of 1, it will be plus a, right? You understand, I am putting values, different values for n in this equation. So first I put 0 and I got this one, and then I put 1 and I get this thing. So h inverse of 1, right, this is equal to, right, and plus, what is the value of h inverse of 0, right? So you understand, we have got this basically h inverse of 0 equals to 1. So that means it will be a times 1, and what is the value of impulse of 1? So it will be 0. You understand why it will be 0? Because impulse has value 1 only when its argument is non-zero, when its argument is 0, right? So impulse has values 0 when its argument is non-zero. So because it's non-zero, so it's equal to 0, so that means h1 inverse will be equal to a into 1 will be a, and if I shift this one, so I will say h inverse of 1 equals to minus a. Okay, so that means, right, so similarly h inverse of 2, right, I'm putting n equals to 2 equals to a plus h inverse of right, you understand, this is n minus 1, so 2 minus 1 will be 1, so this is equal to impulse of n, right, not n, in fact 2. So you understand, this will be equal to 0, right? This is equal to 0. Why? Because the argument is non-zero. When the argument is non-zero, this is equal to 0. So what is right? So what is the value of h inverse of 1? So h inverse of 1 basically equals to minus a. So that means I can write h inverse of 2, right, and plus a, and then multiply by minus a. So this is equals to 0. So a multiplied by a is a square minus a square. When I bring it to this side, it will become plus a square. So that means h inverse of, if I write here, h inverse of 2 equals to plus a square, right? You understand why plus? Okay, because this is h inverse of 2, right? And this will be a into a minus a square equals to 0. So that means right, so you understand, if I bring it to the other side of the equation, it will become plus, right? So similarly, I hope you understand that for h inverse of 3, right, h inverse of 3, can you guess what it will be, or I should do it? Okay, let's do it for 3 and then we generalize it. So h inverse of 3, you understand, I have replaced n with 3, so h inverse of 3, and this is because a times h inverse of n minus 1, so n is 3, so 3 means 3 minus 1 means 2, right, and this is equal to impulse of 3, right? So hope you understand that this will be 0 because the argument is non-zero. Now this, you know, h inverse of 3, and h inverse of 3 means so what is the value of h inverse of 2? So this is a square, right? Positive a square, that's clear, right? So that will be a multiplied by a square, right? I should like, I guess, a into a square. So this is equal to 0, so that means H inverse of 3 basically equals to minus a cube, right? If I write here, so H inverse of 0, right, is equal to 1. Then if I write here H inverse of 3, this is equal to minus a cube. So you see, if n is the 0, right? So if n is 0, this is equal to 1. If n is 1, this is equal to a. If n is 2, this is a square, right? If n is 3, then this is a cube. So can I say this is basically a power minus a power, right? Let me write it. Can I say that this basically this is minus a power? This is minus a to the power, or let me change the color of the pen, so maybe this will be fine. Okay, so let's take this one. Okay, and then I say okay, this is so I was on previous slide but mistakenly. Okay, so we can say that H inverse of 0, it was equal to 1, and so this one I hope you understand. You can write it minus a power 0, right, and this one minus a to the power 1. This is equal to minus a to the power 2 is equal to minus a to the power 3. I hope you understand, right? So 1 means minus a power 0, minus a square, so that we can write minus a whole power 2 a cube, right? So I hope this gives you idea that we can generalize it, and we can say that H inverse of n basically equals to minus a to the power n, right? Because you see, if we have n is 0, so a power 0, n is 1, so minus a power 1, n is 2, minus a power 2, n is 3, minus a power 3. So that means if we have n, then it will be a power minus a power n. Okay, so that's the generalized expression for the causal inverse system, and you understand why this is causal, because for the causal system we say the response is 0 when the argument is negative. So based on that we derived this expression. We said okay, h of n equals to 0 for negative values of n, and then for the positive values of n we found by putting different values, 0, n equals to 0, n equals to 1, n 2, and 3, and then we generalize it. So this is the impulse response of the inverse system. If we convert, right, that will recover x of n from this, right? Originally we have this thing, right, which is y of n equals to x of n minus a x of n minus 1, but we are interested only in x of n because now it's type of distortion factor or distortion that is distorting the original signal, this one, right? So if we have this, if we receive the signal and we have we give it to some inverse system, right? So originally we had this signal and we wanted to transmit it, okay, but due to the multipath the original signal cannot be received at the receive end. At the receive end we receive y of n. And what is y of n? Y of n is basically the combination of x of n. It's delayed and diminished or attenuated form. So this will result into some sort of distortion, right? Now to remove that, we need an inverse system so that we can recover the original system, right? So that's the original signal, and this is again at receive, and we receive the original signal. If we put another system, right, and the received signal, which is now y of n, if it goes through the inverse system, and the inverse system will have impulse response of this, right? So if the inverse system has impulse response of this one, then this will be recorded at the receive end, right? So you can do it by yourself if you just okay. So you receive this thing, and if you convolve this one, so you get if this is convolved, right, the impulse response of this and the inverse system is convolved, so you get the impulse, right? And if you give it input signal fxn, then you convolve with this the response of this one, you get y of n. And if the y of n is convolved with impulse response of this, so you get again x of n. So the next thing is to check whether the inverse system is stable. So you understand that again the impulse response gives the complete information or characterizations or behavior of the LTI system. So if you put the equation for the stability, so the equation for the stability is that impulse response, right, for k running from minus infinity up to infinity, h of k, this should be finite. That means it should be less than infinity, or in other words we say this must be bounded. If this is bounded, then we bounded means that it's less than infinity, right? So we'll get the system will be stable. Okay, if this doesn't give the, if this results into infinity, that means the system will be unstable, right? So we know the impulse response, which is minus a power n. So if I put it here in this equation, so you know it will be something like k running from minus infinity up to infinity, and this is minus a power k, right? So you understand this will give you this will result into some finite value only when yes, one other thing is that we take the absolute value, right? So absolute this, okay. So absolute means whether it's positive or negative, you take the negative one. So if you take this one, so definitely this will result into finite value only when the value of the alpha a, if a absolute is greater than 0 and less than 1. If this is the case, then the resulting system will be stable. If this is not the case, then the resulting system will not be stable. So that's all for this numerical. Let's move to the next one. So here is another example where we have to find the convolution, right? So the input signal is x of t, and it was piecewise function. So it is defined for 0 to 1, it has value t plus 1, whereas from 1 to 2 it has value of 2 minus t, and 0 otherwise, right? So it's easy, and the impulse response is given by impulsive response is given by h of t equals to impulse of t plus 2 plus 2 impulse of t plus 1. So that means the impulse response consists of two impulses. One is scaled and shifted version, and other is just the shifted version. So you can see that it is shifted 2 unit to the left side, because if you compare it with the standard equations, you know that here T naught is basically -2, so -2 indicates the shift to the left side. Okay, so let's first solve it. I think a mathematical solution will be easy for this one. So because we know that the convolution of signal with impulse equals to the convolution of the signal. If the impulse is shifted, then the signal will be shifted, and if the impulse is scaled, then the signal will be scaled, and if it's both scaled and shifted, so the resulting signal will be scaled and shifted version of the original signal. So let's solve it. So we know that y of t equals to x of t convolved with h of t, or we can also write h of t convolved with x of t. So I think better we write like x of t convolved with h of t. So using the distributive property, we can write x of t convolved with maybe something like that here. X of t convolved with impulse of t plus 2 and plus x of t convolved with two times impulse of t plus 1. So we know that scaling, convolving any signal with the impulse will result in the same signal. If the impulse is shifted, so the resulting signal will be shifted. So because it's shifted 2 units to the left, so x of t will be the resulting signal. X of t will be 2 units shifted. So that means we can write it x of t plus 2 and plus this 2 unit scales by a factor of 2, so it will be also scaled, and those 2 times x of t plus 1. So if I plot the signal x of t, so it will be something like, okay, let me this is your y of t, right? So the y of t equals to this. Okay, it's y of t, so y of t equals to this. Now if I plot the x of t, so x of t will be something like, okay, for example, this is, okay, this is 0, maybe this is 1, and this is 2. Okay, so this is your x of t, and this is your t-axis. Okay, so if I plot the signal, it's here t plus 1, so that means t plus 1 is something here. For example, this is equal to 1, and maybe this point says 2. Okay, so t plus 1, so it is something like this, and 2 minus t, so that means that t equals to 2, it will be 0, so something like this. So this is your input signal. Okay, now how the output signal will look like. Can you do by yourself, or you think I should do it for you? So I leave it to you as a homework to plot the second part, that is I have plotted for you x of t, and you're going to plot y of t. So that's your homework. You try it. I hope you can. If you cannot, then maybe I do it for you in the live session. Okay, so here's another group of problem. In fact, we have been given different impulse responses, and we have to find the whether the given system is memoryless or it's causal or stable, and we also have to justify our answers. Right, so I hope that's quite straightforward. Maybe I do some of the problems for you, and I leave the other for you to try. Okay, so these are the problems, and I hope you understand, right? This the impulse response, and this is the shifted step signal, 1 unit to the right minus shifted unit step, or 1 unit to the left. And I hope you can tell whether it's a system with memory. Maybe I just solve for you 1 or 2 problems. I think you can also do it yourself. And okay, let me try this one. Okay, so you understand similar type of problem we also encountered in finding whether the given finding the step response of the system, right? So you understand that the exponential signal of this type, it's actually exponentially decaying signal, right? You understand, if I plot the signal, so it would be something like, not signal, in fact this is the impulse response, right? So that it would be something like this. Okay, it's decaying and it's also decaying, right? And it's okay, so the maximum value it have is 1, and this is your time axis. So at 0 it has maximum value, and when you move away from 0, either in positive direction or in the negative direction, so it will start decreasing. You understand? You can also say from minus infinity up to 0 it is exponentially growing signal, right? And from 0 up to infinity it's exponentially decaying signal. You can also say like this, or you can also say that from 0 you move in either direction, that is positive direction of the t or the negative direction of the t, and you find that the signal is decaying, right? If you look at carefully, you can tell that it's not signal, right? Or you can say it's a response signal, right? So the response signal is basically decaying, and you can also say that basically it is an example of symmetric signal, right? You understand that to find the symmetry, you put a mirror here and you look at into it, and you find its replica this side. So if you look at this one, the replica of this is exactly this one, right? This one. Similarly, the replica of the other side is exactly, let me draw again. So if I say it's something like decreasing, right? There's problem with the mouse, so I cannot. Anyway, so they both will be same. So again, if you put a mirror here and look from this side, you will find the replica of this one, and you see both the replicas are same. So this is an example of the symmetric signal, right? So to tell whether this is a memoryless, so that's very straightforward thing that we have defined that h of t, okay, or h of n for the discrete time case, it should be equal to 0 when t or n is not 0. T or n is not equal to 0. So if you look at carefully, So we defined that h of t equals to 0 when t is not equal to 0. If this is the case, then we say the system is memoryless. But if you look at this one, the system response, it's not 0 for t is not equal to 0. So that means this system has memory, right? This is system with memory. Okay, system with memory. The next thing we have to find is whether this is causal. So for causality, we say h of t equals to 0, right? H of t equals to 0 when t is less than 0. When t is less than 0. So if you look at this condition, you see that it is not met. Okay, it is still non-zero. T is negative, but it has non-zero values. You see these values are non-zero when t is negative, so that means this system is not causal, right? Not causal. Okay, then the next is stability. So we have defined stability as integration from minus infinity, right, up to infinity, h of tau absolute value d tau, it must be less than 0, right? So if you look at this graph, I hope you can go through it and you can find that this system has a finite or bounded impulse response. So when it's bounded, then it is not, it's, in fact this is less than infinity, right? So it's bounded, so that means this system is an example of the stable system. So this we end the lecture for today. I hope the rest of the problems, they are quite simple, and I think you wouldn't have any problem doing those. So that's all for today, right? But you must go all through these problems, right? All of you should do each and every problem so that you can have clearer understanding. Right? You understand what is u of step function and what is step function in discrete and continuous, and what if you have u of minus n. You understand this shows the time reflection, right? Or where you have the time shift, and like if you multiply u of n, so you understand that means this response will exist for only positive values of the n, right? So when n is negative, this response will be 0. So I think you can easily do them, and once you do them, it will give you a lot of confidence, and also it will give you understanding. So if you have any question, you can ask me in the live session. So that's all for today.